correlation coefficient. The learning objectives are to calculate, interpret and conclude correlation coefficient. So why do we use statistical tests? Well, it enables a null hypothesis to be accepted or rejected. It determines whether a correlation is significant. And a statistical test determines the probability of the results being due to chance. So, what is each statistical test? You've got three that we use in A-level biology. The correlation coefficient, also known as the Spearman's rank correlation coefficient. You've got the chi-squared test and t-test. So, the correlation coefficient looks at correlations or associations or relationships between two variables. Chi-squared shows the differences in categoric data. And the t-test shows differences between two means. Now, although we've learned about standard deviation, it's not actually classed as a statistical test. What it does do is it measures the variation in the data around the mean. So today we're looking at this correlation coefficient, looking at if there's a relationship between two variables. So the Spearman's rank correlation test. You would use this test when you wish to find out if there is a significant association or correlation between two sets of measurements. You must have between 7 to 30 pairs of measurements. So we'll look at this example, this worked example. So great tits are small birds. In a study of growth in great tits, the relationship between the mass of the egg and the mass of the young bird on hatching was investigated. Some of the data collected are given below. So the first thing you would have to do is set up a null hypothesis. Remember that a null hypothesis suggests that there's no association, no relationship between the two variables. So there is no association between the mass of the eggs and the mass of the chicks which hatch from them. Okay, the second step is to calculate the correlation coefficient. So you first of all start by ranking the egg mass and the mass of the chicks. So you start with the lowest up to the highest, so they're in order, and then you have to do the same with the chick mass. Now if you've got two that are the same, you would have to say that they were halfway between the two. So if you were saying that that's 1 and that's 2, well 2 plus 1 is 3, so you do halfway between that. So once you've done that, yes, it says note that when 2 or more values are of equal rank, each of the values is given the mean of the ranks which would otherwise have been allocated. So once you've done that, you calculate the difference between the rank values and square this difference. So 1 minus 1.5, 2 minus 1.5, 3 minus 4, etc. So you do that. It doesn't matter if you've got negative values, and then you would square them. Then you find the sum of the square of differences. So you see the sum here is 2.5. Then you calculate this value of the Spearman's rank correlation from the equation. So 1 minus 6 times 2.5, which is what you calculated in the last page, squared, divided by n, which is a number of values, which was, we had 7 data sets, so it's 7 cubed minus 7. So if you put that in again, 1 minus 15 over 336, which is 1 minus 0.045, which equals 0.96. So that is our value of the correlation coefficient. And then once you've got calculated your correlation coefficient, you need to find what the critical value is for the number of values you had. Well, we had 7 measurements. So our critical value for p equals 0.05. We always use the 5% significance. So this critical value for 7 data sets would be 0.79. Well, we can see that our calculated value of 0.96 is greater than the critical value of 0.79. So for the correlation coefficient, you've always got to get a value between +1 or -1. If it's closer to +1, it means there's a positive correlation. If it's negative, there's a negative correlation. The closer it is to 1 or -1, the stronger the correlation. So then you need to interpret this value. So the calculated value of the correlation coefficient is 0.96, which is greater than the critical value of 0.79 from the table. So we reject the null hypothesis, and we can say that there is a significant positive correlation between the mass of an egg and the mass of a chick that hatches from it. And you can also say there is less than 5% probability that this correlation is due to chance. So when a negative value is obtained, you compare the size of the number to the critical value. It doesn't matter if it's negative or positive. It's still an association. It's just that if it's negative, it means they would be inversely proportional. So you get different types of correlation. You've got positive correlation, negative correlation, or no relationship. So what I would do probably first of all is just see from the pattern what sort of pattern you get. Well, there appears to be a positive correlation. As the mass of the egg increases, so does the mass of the chick, and we need to see if this is actually significant. So you first of all rank the data for each variable, calculate the difference between each pair of ranks, square the differences, add up the differences squared, and then you plug it into the equation, the Spearman's rank coefficient equation, which is 1 minus 6 times the sum of d squared divided by n, which is the number of values, cubed minus n. Then you compare the Spearman's rank coefficient against the critical value. So our calculated value is 0.96, and our calculated value is 0.96. There were 7 pieces of data, so the critical value at p equals 0.05 is 0.79. So we can see that 0.96 is higher than the critical value of 0.79, so we could reject our null hypothesis. So you use the RS value, compare it to a critical value in the table to find the probability that the result is due to chance. So, if your calculated value is greater than the critical value, you can reject the null hypothesis. But if the calculated value is less than the critical value, you accept the null hypothesis, and there isn't a significant difference.